Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. I think the other session ran a little long, so we're starting a little bit late. But thank you so much for coming this morning. I'm Krista Savori. I'm the manager of the Quantum Architecture and Computation Group here at Microsoft Research. We're located here in Redmond. And today, hopefully you've come to learn about what we could possibly do with a quantum computer, this new, exciting, potentially revolutionary model of computation. So I am very honored today to be joined by three very distinguished people in our community in quantum computing. We have Matthias Treuer from ETH Zurich. We'll then hear from Eddie Farhi from MIT. And we'll close with a talk from Nathan Wiebe, who is part of the quantum group here at Microsoft. Hopefully, their talks will answer questions for you about what we will do with the quantum computer once we have a scalable, programmable quantum computer. And also, I think it's exciting that definitely in two of the three talks, you'll hear about how quantum computing has lent ideas back to classical computing and about some new algorithms, new classical algorithms that can be applied today that came from thinking about quantum computation and quantum algorithms. So I'm really excited, and I don't want to take too much more time. I want to jump right into our talks. We're going to begin Matthias Treuer from ETH Zurich. He's going to talk to us about, well, what can we do with a quantum computer, but more specifically, what can we do with a quantum computer in the space of material science and quantum chemistry? So Matthias, take it away.
Thank you. Yes, so the basic question is, what would I do if somebody gave me a quantum computer today? That's a question we started asking 4 years back. Since then, we thought we will be able to build one. And the question is, who should fund this big endeavor, which will cost a lot? So why should we build one? And what will we do once we have one? So let's go back to what we can do classically. And classically, it's been 2,000 years from the first machines to the supercomputers, and they can do a lot now. And the question is there actually anything that they cannot do? And we have Moore's law. There's exponential increase in performance, so shouldn't we just wait 10 years and it's better? But when you look at the top 500 list, then it looks good. The top machine just keeps going on up and up and up, but if one looks more closely, then is there the first hint of something going wrong? Is there the first hint of this may be flattening out? There's the problem in scaling. There's the problem in parallelizing to more than a million cores. But more importantly, there's a growth also of the power consumption, and that costs a lot. So how do we go beyond that? That question was asked by Paul Messina at the conference last year. And he asked, what is it that we need to do to go beyond the exascale? And he qualified that, but that he meant not just going to more than 10 to the 21 flops, but to do something groundbreakingly new that is really totally different and is a real game changer, to go way beyond whatever we could do classically. And of course, we here believe quantum is one way to go there. And quantum mechanics is old now, a century old. And we have the first quantum devices around, like we can make quantum random numbers. True, perfect random numbers, that's a little box like this. That costs 1,000 euros. And here, take it around, pass it around. That's the first commercially viable quantum device. A little box that makes money with quantum. Not much, but they don't make a loss making it. And it's Swiss-made. That's important. Then there's quantum communication that nobody can eavesdrop on. There's quantum simulation. There's quantum optimizers. And in the future, we soon have a quantum computer. I don't really know how it will look like, but it will run some version of Windows, I guess. So to start with what is quantum, let me tell you how this quantum random number generator works. And it's a simple device. It has the light source, it has a semi-transparent mirror, and it has two photo detectors. And when you shine light onto it, then parts of the light is reflected, and the part goes through. And if you now reduce the power to single photons, then a single photon also goes partially through and is partially reflected. So it hits it, and then the photon follows both paths. Because it's quantum mechanical, it can go on both paths. But then you detect where it is. And it can only ever be in one place when you look. But which place then is random? In this case, the 0 position here. And that way we get a provably random number if you believe in quantum mechanics. And that can be used to do much, much more. First of all, this is already a qubit, a quantum bit. That's the building block of a quantum computer. A classical bit, you know, can be 0 or 1, and a quantum bit you've heard about, I guess, can be both at once. So it can be in some kind of mix of being 0 and 1. But it's not just a probabilistic state, but it's a coherent way. We say you can make it mixed, and you can undo it. So a quantum bit can be both 0 and 1 at the same time, and that should scare you. That's scared Schrödinger, who then said, okay, that's really crazy. And he had this cat idea. And he placed the cat in a room, and he put a device in the room, a quantum device. And what now happens is, in this quantum device, at some point, and the atom decays, so it gets into a superposition of being decayed or not decayed. So we have it in the state 0 plus 1. Then if the atom is in the state 0, it goes out and it triggers this hammer, which falls onto a poison vessel. It breaks it open, the poison gets out, and the cat dies. But now the atom is in this quantum superposition. It is 0 plus 1. So then also the hammer is in the state down plus up. And the glass is open and closed. And the poison is in and out at the same time. And the cat is dead and alive at the same time. And that's kind of scary and strange, because we've never seen a cat that's at the same time dead and alive. Or me being both here and in Switzerland at the same time, although my students sometimes believe I'm that, because they don't know where I am. But so something is strange here. And what's strange here is that the quantum superposition is a very fragile object. When you start and observe it, when you look, where's the photon, then it's left to right. And when you look at the cat, then the cat at that point is either dead or alive. So at that point, it collapses into one of the states. And so when we see such a qubit, and it's in a state alpha 0 plus beta 1, and I look at the value, I measure it, then it's either 0 with probability alpha squared, or it's 1 with probability beta squared. So the cat, when we look, is always either dead or alive only. So that already shows you how to make the first quantum device, namely a quantum random number generator. You need a single qubit. You put it into the state, and you measure, and you get a random outcome. So this is the first application for our 1 qubit quantum computer. Once we have one, there's the application. But there's more to it. There's something called entanglement. I can take a single qubit and put it into the state 0 plus 1. But now I can take 2 qubits and I can put them into a so-called entangled state. And I found 2 qubits here, the qubit A and the qubit B. By chance, they have them here already at Microsoft. And this is A and B. And I now can take A and put it into the state 0 plus 1. But I can take B and put it. But I can also take both of them and do some magic quantum entanglement. And now they're in the state 0, 0 plus 1, 1. That means they're either both 0 or both 1. But I don't know which one. Now I can take one and I can toss it to Krista. Whoa. And it doesn't matter, these are good qubits. And it wasn't measured, hopefully. But now what we can do, we can now measure it. And if we measure it and I look at it, then I see, for example, I measure it and it's 0. And then I know for sure that Krista, what is your value? 0. No, also 0. We can make it again in the same quantum magic, and I can toss it to Nathan there. Or to Eddie, because it's less dangerous. They're hard to catch, their qubits after all. And now it's 1 here, and it's also 1 there. You see, that's the magic. And he can be in Boston. He can be, and I could be in Hawaii. It doesn't matter. We know for sure that when we measure, we get the same measurement, and it's random. So now we can use that to get us a random secret key that nobody else could know. Now, Einstein didn't believe in that. And he doubted it. And he wrote the famous paper saying that has to be wrong somehow, that there's something wrong with quantum mechanics. But it turns out when you test it, it works in experiments. So it works, we have this state, and we measure the qubit A, and it gives us a random result A, and B, the random B. But they are the same, no matter how far apart I put them. And that's the basis of quantum encryption. We have a shared secret that is secure. Why is it secure? It's secure because while I toss it, for example, I toss it to Nathan over there, they're hard to catch. That if somebody wanted to catch it in between and make a copy, they can't do it. Because while you can copy and clone a classical bit, for example, 0 into 2 zeros and 1 into 2 ones, if we attempt to clone a quantum state, then we can't, it doesn't work. There's a theorem, no cloning theorem, that we cannot clone an arbitrary quantum state. And it's somehow easy to understand. When I measure it, I get a single bit. But to describe the state, I need the full numbers alpha and beta. So I can't really reproduce it from just the measurement. So a quantum state can't be copied. Of course, this is very bad news for programmers because they can't copy my state. And most of our programs always make copies of somewhere, store things somewhere, and they can't do that. I can move it, I can't copy it. So it's a bit hard to think about quantum programming. But it's an excellent use for cryptographers, and it's excellent use for data centers and cloud computing, because I can make my data secure. And nobody can copy it. So let's now look at what we can actually do with more than 1 qubit. When we have 2 qubits, we have 4 possible states. 0, 0, 0, 1, 1, 0, and 1, 1. And it can be all of those 4 states at once. To describe the state, I need 4 complex numbers here. But when I measure it, I only get out 2 bits of information. When I have n qubits, I have 2 to the n possible combinations. The qubit can, in all those 2 to the n states, add once. I need 2 to the n complex numbers to describe the state. But when I measure it, when I look, I only get out n bits. So it's a bit strange. To describe the state, I need an exponential large number of values. But the readout is limited to n bits. So I can work on 2 to the n values at once in parallel, but I have to be careful because at the end I only get out n bits. Let's look at a simple algorithm of what we can do with that. I want to take a function and I want to to evaluate the function on multiple inputs at once. So here's the function f, and there's the input x, and the output here is the function of x XORed with the value y here. So I can call the function on 0, I get f of 0, I can call it on 1, I get the function at 1, or I can call it on the superposition, and I get a superposition of the answers. So I have all the answers there at once. Now you could think this is exponential speedup because I have an exponential parallelism. And that's how it's often portrayed. But there's a problem here. What happens when I want to read out the answer? When I want to read out, I get only one particular value. When I read out for x, I don't get the superposition. I get either 0 or 1. And then what I get is just the function evaluated at a random value. Wait, that wasn't very useful. I can do it, and it somehow has all those values stored in there, but I can't access it. I read out, and I get only one random value. That doesn't help me. Unless I'm smart. And I have to be smart, and I have to make use of those values that are stored in there, inaccessible, and compute something from them, like the sum or product or maximum or minimum or something, and then read out only that one global value. And here's the first simple quantum algorithm. I can use that to actually, when I then calculate, for example, the XOR of the values, to determine with a single function call whether the function is constant or not. Classically, determining this needs two function calls. Quantum mechanically, I can do it in a single function call. Now that's something that we can never ever do classically. There's the lower bound classically. It's two function calls. Quantum mechanically, the Deutsch algorithm does it in one. Now, you might not be very excited, because honestly, I have not found a use for that yet. So let's make a short break here, an interlude. Where are we with quantum hardware, and what can we do? The problem was that we need to build a qubit. And the qubit is like a Schrödinger cat. And we know you've never seen a Schrödinger cat. And the problem is we have this beautiful evolution here, but the environment or something somehow observes it. There's always this dragging around the environment. Something, maybe a photon, maybe somebody shakes it, a sound wave, observes it, couples to the quantum system, and basically measures it. And then our nice quantum evolution is gone. So we need to really build something that is totally decoupled from anything in the universe, but I still have to be able to program it. And that's tough. And people are trying since decades now. They've made progress. For example, using ion traps in Innsbruck, they have 20 qubits, can do about 100 operations there. Then there are superconducting qubits, there are quantum dots, there are defects in diamond can be used as near qubit, or the Microsoft effort here focuses on topological quantum bits. They don't exist yet really, but once they are, they will be much, much better than anything else in the world. It might be a few years to have one clear qubit here, but then their progress will be fast. So in the meantime, I use my laptops, for example, to simulate a quantum computer. And how hard is that? We need 2 to the n memory and time to simulate it. So if I want to simulate 10 qubits, it needs microseconds on a smartwatch, 20 needs milliseconds on a phone, 30 needs seconds on a laptop, 40, I'm talking minutes on a supercomputer, 50, I want the world's biggest machine for a few days, 60 qubits, I want to wait a couple of decades, and 80 qubits, I can estimate that to build a machine where I can store the state of 80 qubits, it has to be as big as the visible universe, and the single operation will take as long as the age of the universe. So once we get to about 50, it gets hard, and once we're at 80, then this can do things that no classical computer can ever do. So if you ask the question, why should we build a quantum computer? Then it seems to be very easy, because we can, and it can do things that no classical computer can do. And we can build it, so of course let's do it, even if it costs a lot. And if you argue, okay, it might at the end cost as much as a classical fab, which is several billion, then the answer is somebody smart will figure out what to do with it. And for classical machines, people didn't believe that one could sell more than 5 machines, and they were wrong. So also for quantum computers, once we build them, smart people will find a use. But if we want to put in lots of money now, we need to have a bit more of an answer as that. So what I want to now focus on is the question to go beyond exascale. What are the things that we really cannot do on classical computers? So what are the problems that we can solve on a quantum computer, but that we can never solve on the fastest classical machine that we could build with the same money in the next 10 years? That's a big challenge, and that question has been asked first by Microsoft and now by many other companies as well. And when you ask people, they tell you, okay, it's no problem. There are lots and lots of problems that we want to solve. Better drugs, counter climate change, cure cancer, fight hunger, fold proteins, better batteries, and so on. There are lots of problems that people tell you. But when you step back and look closer, then this is just a wish list of what we want that a quantum computer might do. But what we actually want to look at is what can we actually do. So which problems can we actually solve? D-Wave built a machine, a quantum machine. According to Time magazine, nobody knows how it actually works. But they hope that it could solve hard problems faster than a classical one. They built an amazing device to solve quadratic optimization problems. These are NP hard. They scaled it to 1,000 qubits. This can be built with bad qubits. The problem is, for such a strategy, nobody knows how fast it could ever be if you build it perfectly. And so far, one hasn't seen any scaling advantage. It does not solve them better than a classical machine. So we want to look at problems where we know that a quantum machine will have an advantage. And there's a whole list on the net of about 50 quantum algorithms. But most are math problems, abstract math problems. And we need to look kind of how can we turn them into real application problems. And one is Shor's algorithm for factoring. You can factor a small number easily. Factoring a large number is classically hard. I know that only because I multiplied the numbers beforehand. On a quantum computer, this is easy. So this could now be used to factor numbers. Why is that interesting? That can be used to crack RSA encryption within minutes to hours on a small machine even. Is that a long-term application? I don't think so. First of all, because there are few people who want that. And secondly, once we can build a quantum computer, we will quickly switch to encryption schemes that cannot be cracked by quantum computers. So then that stops being an application. Let me now then jump quickly to what we really want to do or can do. And one thing we know we can do, because that's what quantum computers were invented for, we can do quantum physics on quantum computers. Feynman said, if you want to solve quantum problems, which are exponentially hard, use quantum hardware to do it. And of course, as a quantum physicist, that's great for me to have, but why would a company build one for that? And the answer comes when you look at what do we actually use classical machines for. And the first 5 codes that broke through the petaflop barrier were all codes that did material science, quantum chemistry. They solved quantum mechanics for materials. So these are the big problems on classical supercomputers. And for many problems, the classical codes are good enough. But there are also many other problems where we don't know how to solve them. For example, a room temperature superconductor, we don't know how to actually design them because that would be exponentially hard on a classical computer. The non-toxic pigments of certain colors, like a nice yellow that's non-toxic, that's a hard problem. Catalysts. There are many, many hard problems here that we cannot solve on a the classical machine, but where a quantum computer might help us. And so we then ask the question, can we do quantum chemistry and material simulation on a small quantum computer with people here at Microsoft? And first we ask, can something that is classically hard be solved on a quantum computer, on a small one? We quickly change the question, can it be done on a huge quantum computer, on a science fiction style really big one? And we had a bad surprise at first. And that surprise is, now that's the only technical slide I'll show. It is a very complex model we have to solve, where when you have n electrons, you have n to the 4 terms. And we need to time evolve with these n to the 4 terms. So let's say we have 1,000 electrons, then we have about 1,000 to the 4 terms. Now for each one, there's an efficient algorithm, but in total, the scaling, okay, it's polynomial, so with 1. Great, with 1, because we have a polynomial scaling algorithm for an exponentially hard problem. But the power in a naive way is about n to the 9. And is that really good news? We then calculated how long would it take to solve kind of the smallest problem that one might want to do, and the answer was 30 years on an amazingly fast machine. And then information theorists would declare victory, saying it's polynomial, so it's efficient. As an application scientist, I don't want to wait 30 years. What do you do when you have such a bad scaling classically? You improve your algorithm. You look for better ones, you parallelize it, you vectorize it, you pipeline it, and you really use all the tricks you know to get the scaling down and the constants down. And with great people here, we did that. We got factors n in reduction on various ways, and in the end, got the scaling down by a factor of about 1,000 n squared. And now the runtime estimate is down to minutes. Now it's really doable. And now we can do nice things with it. One is, for example, we could look for catalysts for nitrogen fixation. The problem is, how do you make fertilizer? Right now you take methane, and a big fraction of the methane mined on the Earth and air, and you press it together, heat it up. It costs lots of the energy, and is quite expensive. But in the root system of some plants, there are bacteria that can do it much, much cheaper. However, nobody knows how they do it. The structure of what they use is known by now, but nobody can solve it. If we had a quantum computer, we could simulate it, understand it, and then use it in an industrial process to get the better catalyst. Same then for materials, superconductors, and so on, that we could do much more if we had a quantum computer. Just for the outlook, there's even more. If you have a quantum computer, you can do cloud computing in a secure way, so that the person who runs the cloud can't even know what the program is you're running, or the term you search for. And of course, Google doesn't like that, because they don't like that they don't know what people search for in their search engine. There's Quantum Money by Fahy, who's here. So there are many, many more ideas. We thought of quantum wedding bands last night at dinner. So there's much more we can do. The quantum games is still the open challenge. So if you have a single quantum bit, you can sell already now a quantum random number generator. With a few, there's a quantum encryption. With many, it looked hard at first, but now we have the first application. And I want to end that what we really need is we need quantum software engineers to look at getting more applications. This should not be just the field of your theory, but we need more people now who write codes for machines that we'll only have in 10 years or 20 years. But we need the codes now to learn what we build in the code design way. Thank you. And those are the people who helped us.
Great, thank you so much, Matthias. We're going to hold the questions till the end, and we'll have roughly a 10-minute Q&A after all of the speakers have gone. Next up, we have Eddie Farhi from MIT, and he's going to tell us more about how to use quantum computing for combinatorial optimization. Okay. So let's welcome Eddie.
Well, thank you. Can you hear me? Well, you know, wait a second. Introduction, keyboard setup assistant. What? Go away. Thank you. Well, thank you for having me. And I didn't coordinate with Matthias, so he stole like half my talk. So it's kind of bad, but I'll try to figure out what to do. But I'm going to be talking, and also he ended with a plea for the development of software, and that's really what has interested me mostly, which is my interest in this field has been really, what would you do with a perfectly functioning quantum computer? So I'm a little bit less worried about the implementation, and rather just asking the question, if you had a perfectly functioning quantum computer, what would you do with it? Now, I do have my beginning slide about qubits, so I'm just going to repeat a little bit of this because I need it for my own uses. Again, a qubit is a quantum bit, and you can think of it as any two-state quantum system. This is the basic building block of a quantum computer. It's this this very simple thing you can think of is the spin of an electron. You know, you learn in chemistry that the electron can either be spin up or spin down along a certain axis. That's how you fill shells. Well, those two spin states, you could think of up as a 0 and down as a 1. But the thing is that if you orient the electron spin in a different direction, it can be in a superposition of the two. And this is mathematically described by saying that there is a vector in a little two-dimensional Hilbert space associated with 0 and a little vector associated with 1, and the state of your quantum system can be a superposition. Alpha and beta are complex numbers, and the sum of the squares of them are 1. This means the complex number times its conjugate. And as Matthias pointed out, alpha squared is actually the probability that a measurement will make a 0. Now, a qubit is a really strange thing, right? Because, you know, if you think about an electron spinning, it has angular momentum. And what the spin, when we say it's quantized, we mean that the z component of the angular momentum is always measured to be either plus h bar over 2 or minus h bar over 2. And think about that for a minute. You have a vector, and I tell you, no matter how you measure it, the component of the vector is always going to have only one of two values. That's kind of crazy, right? Because if you think of a vector, and if I orient my vector this way, you would think I could get a 0 component, and you can never get that quantum mechanically. So the most basic building block of the qubit is something which has no classical description. And I think that's something we should never forget, that the most fundamental building block of quantum mechanics cannot be described classically, and that's a spin-a-half particle. Now, what's crucial in quantum computing is superposition, which means that you can be in a state of two different things at the same time, and interference. And interference means that these numbers are not positive numbers, but they are complex numbers. They can be negative real numbers. And the fact that you have minus signs is what drives quantum computing. Now, a state of n qubits, instead of having one, I can have n of them. But then if I have n qubits, then that Hilbert space, or the theory, is described by 2 to the n complex numbers. And as Matthias was already pointed out, that can be huge. If n is 100, 2 to the 100 is what I call beyond cosmologically big. You don't see numbers in cosmology of the size 10 to the 100. If you ask how many photons are in the visible universe, it's only like 10 to the 80. So you can quickly get to numbers which are beyond cosmologically big. And once you have a bunch of qubits, they can be entangled and have non-classical correlations. And so this is a quantum computer right here. It's a bunch of spin-a-half particles, which I'm going to manipulate to get an answer to a computational problem. Now, I want to say one other thing, which I always feel compelled to say to an audience of computer scientists. See, this equation here is called the Schrödinger equation, and it is the equation that tells you how the system, a quantum system, evolves in time. I is the square root of -1, h bar is Planck's constant. This says the time derivative of the state vector is a certain operator called the Hamiltonian times the state vector. This gives you the forward evolution of any quantum system. What's required in describing a system is specifying the Hamiltonian. But this equation, no violation of this equation has ever been seen, and it can be used to correctly describe chemistry, materials, properties of light, everything that goes on at the LHC. If you look at, let's say, the production of the Higgs boson, that's described by quantum processes, nuclear physics, bombs, everything. So, you know, sometimes computer scientists like to think that quantum mechanics is just some other model of computation, which we do not have to take seriously. You're wrong. You have to take it seriously. It describes nature. And there's no violation of it ever seen. Some people are uncomfortable with it. It's too bad, you know. You know, so that's the end of that. Now, quantum computing, so what's the idea in quantum computing? The idea in quantum computing is to accept the fact that nature-based is quantum mechanical, base the logic system, the logic of your computer on quantum law, and then ask whether you can find algorithmic speedup. And again, what we mean by algorithmic speedup is reducing the number of steps to go from the input to the output. So if you can do that, if you can vastly reduce the number of steps required to go from the input to the output, then if you even have a slow quantum computer, it has a slow clock speed, it might outperform a very fast classical computer. And a beautiful example, which was mentioned with a nice picture of Peter, was factoring, where Peter Shor showed that if you have a d-digit number, and, you know, so think of D as 500, the kind of numbers that are involved in crypto systems used today, it turns out that the quantum algorithm will require of order d squared steps to factor the number, but the best known classical algorithms are all super polynomial in D. Now, there could, of course, exist a faster classical algorithm, and the person who has it is off breaking codes and getting rich or something, but that's the best known, is super polynomial in D. And so this is a beautiful example where quantum mechanics can be used to solve a problem that in number theory, which seemed, you know, when I saw that you could solve a problem in number theory using quantum mechanics, I was very impressed with the fact that quantum mechanics could do that. And of course, this is the great example that people always refer to. But anyway, I would like to talk about a different set of problems that people are interested in, that I'm in particular interested in. These are optimization problems. And optimization problems are ubiquitous in computer science. And computer scientists abstract them into and talk about complexity classes. This is not really computer science, it's computer math, but they call it computer science. In this case, so let me tell you, give you an example of this. And what we're talking about here is called combinatorial optimization. So in this case, some of you know this, but I'm going over it because people like to hear what they know. It makes them feel smart. You know, here you have n-bit strings. So the strings are strings of bits which can take the value 0 or 1. I'm calling them z. And then we have some kind of cost function. And that cost function, which depends on these, is a sum of terms. And each term in the sum, m you can think of as of order n, it may not be too big. Each term in the sum is called a clause, which acts on a subset of the bits. So it looks at a subset of the bits, the first 3 bits, let's say. The first 3 bits can take 8 values. And it says certain of those values are true, certain assignments are true and certain aren't. And the cost function is then 1 if those on the assignment that satisfies and 0 on the assignment that doesn't. Okay, and the prototypical example of this is something like 3SAT, where you have particular form for the clause. Every clause involves 3 bits, and they're always of a certain form. I'm going to talk about a different kind of problem in a moment. So anyway, the task at hand is to maximize this function. Now, of course, that is that's the mother of all computer science problems. Maximize this cost function, because if you could maximize it, then you could, and know the actual maximum, you could, for example, determine whether there's an assignment of the bits that satisfies all the clauses, and then you would have solved 3SAT or any other combinatorial optimization problem. So that's very, very difficult. So, but what we're going to be interested in is not finding the absolute maximum, but an approximation. In other words, we want to find a string z that makes C of z, for the string z, over the maximum possible value as big as possible. As big as this could be as 1. But maybe you'd be happy at 3/4, or maybe you'd be happy at 10 to the minus 5. I don't know. Depends on your needs. But obviously, approximate optimization in many real-world situations can be just as useful as exact optimization. Actually, I made a presentation at the Simons Foundation, and Jim Simons was there, and I said approximate optimization can be just as useful as actual optimization. He said, I know that. Jim Simons says, forget it if you don't. I bet he did. Anyway, so what we want to do is make this, and this is still hard, and I'm going to tell you how hard it is, and there's been a lot of progress in computer science in the last 10 years and 20 years discussing how difficult it might be to find solutions to approximate optimization problems. And I think this is a fascinating area of study, and I think it's also an area where quantum computing may have things to say. So this is my sort of global picture of combinatorial optimization, but what I would like to talk about is a more specific, just a single problem, because I believe in, proof by example and, just look at one case. Okay, so I'm going to look at a problem called max E3 ln 2. What do those words mean? Well, I want to maximize something, and I'm going to explain what all those things mean right now. So this is a problem where I have n variables, so I have n bits, and I have m equations. And each equation is exactly of this form. It involves 3 of the bits, and I tell you that the sum of the bits needs to be mod 2, 1 or 0. So I might say, okay, bits 1, 9, and 10 should sum mod 2 to 0. And bits 1, 9, and 107 should sum up mod 2 to a 1. So the way I specify an instance is by giving you a collection of triples, telling you which bits, and I tell you whether for each triple, whether it should sum to a 0 or a 1. Okay, that's the problem. Now, first of all, the task is now to find a string that maximizes the number of satisfied equations. First of all, this is an interesting problem because you can determine immediately if there's a string that satisfies all the equations. That's because these are linear equations, and you can just do Gaussian elimination and solve it. So you can determine if there's a solution, but just by doing algebra. So that's not what I'm interested in, that case, because that case is too easy. I'm interested in the case where there are more equations than variables. There is no solution. And the task now is to find a string that maximizes the number of satisfied equations. That's my goal, satisfy as many equations as possible. Okay, now that task is NP hard. In other words, it's as hard to find the optimal solution for this problem as it is to solve the traveling salesman problem or 3SAT or any of your favorite NP-complete problems. So it's very, very hard. So we're not going to do that. We're going to try to find a good solution. Okay, let's try to find a good solution. So how hard is that? Well, so let's take, so now what I'm going to do is approximate optimization. And I'm going to give you an algorithm for doing that. The algorithm is guess a random string. I just guess a string, random. I pick each bit with 50% probability randomly. Assuming I have a real number, I can have provable random number generators, but Matthias gave us one today. I can use that device, generate real random numbers, and then I can solve, and then I can plug it in, and you'll see, I think you can see, that you'll satisfy half the equations. Because if you take any one of those equations and you randomly put down the bits, it's going to sum to a 0 or 1 with 50% probability. So that gives you a 50% algorithm. So there's guessing gives 50%. Now, amazingly, if you could produce an approximation algorithm, 10 minutes, okay. Amazingly, to me anyway, if you could produce an approximation algorithm that gives a half plus epsilon approximation in polynomial time, where epsilon is any fixed constant, 10 to the minus 50, then p equals np. So I think that's a very amazing result, because it says that the slightest improvement on guessing is extremely hard. Okay, that you can't do better than random guessing. And when I saw that, I said, this is a really fascinating problem because of that limit right there above random guessing. So now we're going to try to make a little more progress on it. And what we're going to do is I'm going to give you a little more information. I'm going to tell you that every variable is in no more than d equations. So now I've given you something. Before I gave you nothing. Now, once you do that, I tell you that every variable is in no more than d equations. Then there is a classical algorithm that was written that came out in the year 2000, which gives a half plus a constant over d for the approximation ratio. It will produce a solution which has that approximation, a half plus a constant over d. Now, of course, you see, I've given you something. I've told you no equations more than, so it doesn't violate this, because this said, had to work all the time. So then we then developed a quantum algorithm, and in late 2014, we got a quantum algorithm for this problem that gave a half plus a constant over d to the 3/4, which is an improvement, because for large d, this is bigger than this 1 over, okay? So we improved it, and then that sort of set off a real interest in this problem in the classical computer community, and a total of 10 plus 1 making 11 classical computer scientists then got together and came up with an algorithm that got a half plus constant over d to the 1/2, which came out about 2 months ago. And you know, there were 3 of us and 10 of them, but that's okay. So, so anyway, what did we do? We then went back, and okay, so this is also the algorithm. It's called the quantum approximate optimization algorithm, and this is me and my close collaborators, Jeffrey Goldstone and Sam Gutman, just in case you ever hear of Goldstone bosons. That's Mr. Goldstone, my collaborator. Anyway, so what we did is we took we redid our analysis, we tightened it up, and now we have a half plus 1 over 101 d to the 1/2 log d. And so what we did is, so we still have the log, but we improved it because this is better than 1 over d to the 3/4. But we could also show something else, which is that in the typical case, we get a half plus 1 over 2 square root of 3 d to the 1/2. And that means that if you, and what I mean by a typical case is this. If I give you a fixed set of triples, and then I randomly select whether the bits should be summed to 0 or 1, then that's what I mean by then in that case, with very high probability, you're going to find the solution in this much time. I can explain it, more technically. But so we have this in the typical case. So we're not really sure whether this is just a weakness of our analysis or whether we're really stuck here with the quantum computer, we can't do better. I don't know, because it's very recent. So can we get rid of the log D? Now, maybe we can, but you got to be careful. Because if you get rid of the log D, but the constant is too big, then there's another fact here, where if there exists an algorithm, and if I should say a polynomial time efficient, all that algorithm stuff, which can achieve a half plus a constant over d to the 1/2 for a sufficiently large constant, then p equals np. So we're getting very close to the barrier of what is probably doable now. So, so now, well, I guess maybe I'll move on to my next slide. Oh, yeah, I want to tell you how the algorithm works. I forgot to do that. So, yeah, let me do that. So here, suppose you have a single qubit. It's easy to make a qubit which is 1/√2 0 plus 1/2 1, and we've already discussed that. Now, if I have n qubits, which are each of this form, then notice that if I have the n qubits of this form, that can be viewed as the uniform superposition over 2 to the n possibilities. Because when you multiply this out, you get every possible combination of 0 and 1. So it's very easy to start in the uniform superposition. I see you 5 minutes, that's perfect. It's very easy to start in the uniform superposition over all possibilities. But note, when you do that, when you start in the uniform superposition over all possibilities, then if you measure one string, you get that string with probability 1/2 to the n. It's just like guessing. So the starting point of our algorithm is this. Now, the next thing we do is we're going to call the cost function with the quantum computer. The cost function, C of z, is the number of equations satisfied by a string. And that is easy to compute. If I specify the instance, it's very easy to calculate how many equations are satisfied by a string. Because I have the equations, I just check them. So and then, since it's easy to compute this function, it's actually easy to execute in the quantum computer to implement the algorithm e to the I gamma c, where gamma is a real parameter. What does this do? This unitary operator, acting on a single basis state, puts the phase in front of it, e to the I gamma c. This is a number whose modulus is 1. I is the square root of -1. Gamma is a real number. C of z is the value of the cost function on z. Now, if I start in this uniform superposition of all possibilities, and I act with this operator, I get the superposition over all things, but everyone's phase has been altered. And what I've done here with the quantum computer is with one call of the quantum computer, I've altered the phase of every element of the superposition. So one shot, I've hit every phase. Okay? So with one function call, we change the phase of 2 to the n states. That's good. Now, there's another step in the algorithm, which is I'm going to take a single qubit rotation. I can take a 0, which is like an electron spinning in this direction, and I can rotate it. A very simple way to do that is put on an external magnetic field if you actually have a physical electron, and you can rotate it. And when you do that, the 0 goes to cosine beta 0 plus I sine beta 1, and 1 goes to I sine beta 0 plus cosine beta 1. So I can rotate individual qubits. So now consider the operation where I rotate every qubit by beta. And that's also very easy to implement. So here's the algorithm now. Pick a gamma and a beta. Take this initial state, which is the uniform superposition. First act with the cost function unitary, then act with this and measure in the z basis. So it's two operations. I start in the uniform superposition, I apply this unitary, and then this one, and then I measure. And what we were able to show is we were able to show how to pick gamma and beta so that the observed string z will satisfy that many equations. I can't really show you how we did that. It's just math. It's just a bunch of math. Now, but I think what's good here is that this works for all instances of E3 Lin 2. So this is really the first time, I think, that we have a result in quantum computing where on combinatorial optimization where we can prove something about every instance of a problem. Because there are other cases, like when you talk about a quantum adiabatic algorithm or something which is a heuristic. We hope it's going to work, but here we know it's going to work because we can prove things. Now, the other thing is that we can actually, we also had we could also prove that we got improvements on guessing for max cut. But if people know about that, you know, if you know what max cut is, if you randomly guess for max cut, you get a 50% approximation. But then Gomans and Williamson came along and showed how to do better than that. So we do better than guessing, but we do not yet beat Gomans-Williamson. But we're working on that. But anyway, there's another way to extend the algorithm, which is to do it again. In other words, act with U with an angle gamma 1, then act with V, but then act again with U, and act again with V, and act again with U. And every time you do this, you can also prove that this can only improve the performance of the algorithm. And in the limit as p goes to infinity, it actually works perfectly. So you can have layers of this algorithm which only get better, and in the infinite limit, it's perfect. But the infinite, you know, I'm not that interested in the infinite limit. I'm hoping that with low values of p, we can do well. So far, we've only analyzed p equals 1. Okay, so now, so now the future. The future, I want to go to higher values of p. I want to look at other problems. I'll tell you, see, the problem that we looked at, E3 Lin 2, wrap up, okay, great. The problem, I'm on my last slide. The problem, if you look at E3 Lin 2, you're at the p versus np boundary. It's very tough. But there are other places you can be at the unique games boundary, which are also very interesting. So anyway, what I want to do, though, what I want to advocate is to run this algorithm on a small quantum computer to study its performance. And the reason for that is that this algorithm has very simple gates and has very low circuit depth. And it may not need error correction. And what's one thing I intend on Friday when I'm spending the day with the team at Microsoft, which is very interested in actual implementation of quantum algorithms, in quantum compilers, et cetera. I want to spend time talking about the possibility of figuring out how you would actually implement this algorithm on a machine. And that's it. Thanks. Oh, yes, this is, I guess. Great, thank you.
Great, thanks, Eddie.
Sure.
So next up, we have Nathan Wiebe, who is from Microsoft, and he's going to tell us more about machine learning and how quantum algorithms can help improve machine learning algorithms, and also a new classical machine learning algorithm.
Okay.
So let's welcome Nathan.
Well, thank you very much. I'm really happy to be here and apparently lose my slides. Awesome. Yeah. All right. Well, okay. Let's hope decoherence doesn't strike again. So, that's where my actual dongle was. Okay, great. So today I'm going to be talking to you about some work I'm really excited about, showing how you can use quantum computers to accelerate certain tasks in quantum deep learning. But similar to Eddie's talk, I'm not just going to talk about that. I'm also going to talk about how ideas from our algorithm actually ended up giving back to machine learning and providing new methods for training deep Boltzmann machines on classical hardware that, in some cases, have performance advantages over traditional methods like contrastive divergence training. So, I'm a member of the Quark group, which is part of Microsoft Research's quantum effort. And Microsoft has been sponsoring quantum technology since nearly the beginning of the game. And right now, we've got a rather large contingent focused on the hardware, largely at Station Q, as well as quantum software applications, where we look at algorithms similar to largely what Matthias was talking about, as well as a little bit to what Eddie was talking about. And in particular, we're very, very interested in quantum chemistry simulation algorithms. We're interested in quantum compilation problems, cryptography problems, and also machine learning. So I'm going to be talking about machine learning in this talk, obviously. And so before delving into details, I'd like to give you guys a bit of an intuition at a high level about what are the sorts of things that are interesting in machine learning. So typically, what we'd like to do with machine learning is we'd like to be able to train a computer to do the things that come very naturally to us, to recognize and reason about objects in the world around us, and do so in some big picture way, rather than coming up with a bunch of kludgy hacks that are only designed for one particular problem. Come up with broad frameworks that we can use to train to attack wide ranges of particular problems. So for example, one of the things that that you might want to do with this is handwriting recognition. For example, US Postal Service needs to come up with automated systems to read addresses that are sent in. So they need machines in order to be able to do this expediently. And so in this case, how you would train a computer to do this is you would start with some model. This is an abstract model that could describe a whole bunch of different things, but you'd like to come up with a model for handwriting. So you start with a big training set of examples of handwritten digits, and you would feed this into a training algorithm, which then gives you a trained model for this. Now, once you have this trained model, what you'd like to do is you'd like to generalize. You'd like to go beyond the examples it's seen and use this trained model to classify or generate examples that it hasn't seen. And so how this process works is something like this. You have this trained model, now you feed in input images. And this trained model takes those input images and ideally reads them and gives an output number, which should match those. So that's the idea for how you could use a machine learning solution like this to classify. Similarly, you can use it to generate examples. And this is, of course, a very important application. So naturally, it ended up spawning a lot of interest in the quantum community about whether quantum hardware could be used in order to accelerate some of these really important tasks. And this, in contrast to quantum simulation, which really began in a proposal by Feynman in the 1980s, quantum machine learning is relatively new. The first kind of concrete proposal to take a look at it was only in 2006. And since then, there's been an increasing number of algorithms that people have looked at for it. But the broad strokes intuition behind all of this, really that I think is amazing, is that in machine learning, often the first-class objects that you want to reason about and you want to manipulate are themselves probability distributions. Classical computers can't manipulate probability distributions directly in a nice way. Instead, we usually have to manipulate samples and implicitly deal with the probability distributions. But as Matthias and Eddie suggested, a quantum computer can directly manipulate quantum states and, in turn, probability distributions. So this gives you a much nicer framework to approach these problems. Also, the other thing that's very nice about it is that quantum computers give you access to certain linear algebra applications. For example, they can do operations on systems of equations that give substantial speedups, and in some oracular settings, even exponential speedups over the best-known classical algorithms. And so there's a lot of reason to suspect that quantum computing can provide huge advantages. But so far, most of the examples that have been looked at really aren't for the most kind of commercially or scientifically interesting classes of machine learning algorithms. And this is one of the things that really prompted us to try to take a look at deep learning, which, as I'm sure many of you know, is all the rage. Now, I should also mention that unlike many of these other applications, speed is not the only thing. I emphasize this because classical machine learning algorithms for many of these things are plenty fast. But the problem is that they require a lot of unwieldy approximations in order to get them to work. And sometimes these approximations can be wildly inaccurate. So it isn't enough just to provide a speed up for these algorithms. We also want to be able to provide richer models that more accurately capture things, or ways around the messy approximations that are needed to get existing machine learning algorithms to work. So with deep learning, the reason why this was a natural target for us is because of the fact that it's basically led to a revolution in machine learning and artificial intelligence. One of the big news releases was this, when Microsoft announced that deep learning can be used in order to allow real-time translation between English and Mandarin. And this again hit the cover of the New York Times. Also, in the news, human performance has actually been able to be exceeded for ImageNet classification tasks using deep learning. And this is remarkable because it's one of the few examples that has been shown of a computer system actually being able to exceed human performance for a complex image recognition task. So these are pretty amazing approaches, I think. And what's the general intuition behind deep learning? The deep learning tries to mimic how well, at least how I believe I see the world around me. And so let's say I'm trying to look at a car. How do I reason about whether some image is a car or not? Well, often what I'll do is I'll look for high-level features that are indicative of carness in some abstract sense. So I don't look at this and look at each of these individual pictures and pixels and compare it to some filter that roughly describes a car. I say, hey, this thing's got a bunch of tires. It's got doors, rear view mirrors. That looks like a car to me. All this reasoning is based on high-level features that are inferred from the data. And that's the idea of deep learning. What you do is you go through and you infer features from raw data and come up with a hierarchical model for this, and then only reason on these high-level inferred features rather than the raw pixels that constitute the image. And this approach is also very useful for confusing images like this one. If you take a look at this, there's some features here that are totally bizarre. You really don't expect dogness to be correlated with hatness over here. Most training data, unless you scour the internet, will not have too much of this. Yet, deep learning does a very good job of partitioning these images and recognizing that these are disparate concepts and should be viewed as two separate objects. So deep learning has proven fantastic for these sorts of tasks. Now, there's a bunch of different ways that you can approach deep learning. And from our perspective, we had to pick one. And the one that was perhaps most natural was for quantum computing is to look at the Deep Boltzmann machine. So the Deep Boltzmann machine can be motivated on many different levels. From the perspective of people in AI, you can imagine this as just a class of recurrent neural network, where each of these dots that I've drawn in this graph represents a neuron. And whether this neuron activates or not depends on whether or not all the other neurons that it's connected to are firing or not. And these lines in here refer to connections. And these are each given an individual weight. Whether it's positive or negative depends on the particular application. And your goal is to find these weights in order to come up with a model that's likely to generate your probability distribution over training examples that you fed in. So that's it. You want to make this thing maximally likely to generate your training examples. For those of you who have a physics background, you can think about this system as really just an Ising model in thermal equilibrium. And we want to train the interactions in the Ising model in order to maximize the probability of generating the data that we feed into it. So that's the idea. Now, there's a couple of different classes of units here. So first thing is that we have these down here. These are called the visible units. This is where your input and your output for the algorithm sit. This is you can imagine this is from the perspective of a user staring at the 1,000-meter view of this. That this is about all that you actually end up seeing. These hidden units over here, these generate the higher level features that I was mentioning that you generate to analyze, say, an image. These higher level features are called hidden units. And really, from the 1,000-meter view of this, these are designed in order to generate the appropriate correlations between the input values that you have at the bottom. So that's basically it. And one of the things is that, if we're talking about image recognition at the raw level, the input data could just be a pixel. It could be an image bitmap. Then the Boltzmann machine could infer edges from this at the next layer. Then higher up, it might look at textures. And then at the highest level, it might look at object properties like the grills or the rear view mirrors, features like this. But one of the key features about this is the conditional phrase that I used, could. In order to make deep learning successful, one of the most important things that we ended up finding, or people ended up finding, is that it wasn't good to tell it to look for edges. It wasn't good to tell it to look for textures. The key was to let the computer decide what actually is the best representation to do it. Now, this is a finicky algorithm in order to try to get it to automatically detect what are the right things to infer about. But that's the whole idea. And this is what led to this revolution in image processing and speech. This ability to take a step back and teach the computer how to learn these features rather than telling it what's important. And so for our cases, of the only things, other things that I wanted to mention is that the training process really just involves changing these connections here as well as on-site bias terms. But another feature that's very important is a concept called regularization. And so if you have a big enough network here, then you can just set these weights so that it memorizes all of your training examples. All of them will fall out of this with 100% probability. But that's not what you want. It's like training for the test. The last thing you want if you want to teach a student, say, mathematics, is to memorize every single derivative they could possibly end up seeing on the exam. Instead, you'd like to teach them the high-level concepts behind it. And so deep learning, you have to stand on a knife's edge where you're fighting between not being able to learn anything and memorizing too much, because both of them can be fatal. And this concept of regularization, i.e. giving a penalty for having very strong correlations between these units here, is essential for making this work. Okay. So again, the key point is that these deep Boltzmann machines really can be just thought of as a class of neural networks or Ising models in thermal equilibrium. The other thing that's very interesting about Boltzmann machines is that they're actually form a generative model. So here's a really cool set of Boltzmann machine that was trained by Hinton, and I've never been able to pronounce his name, but what's his name here? So anyways, they trained this Boltzmann machine, which consisted of a few thousand hidden invisible nodes, using these figurines over here, images of these figurines. And then they got it to draw, essentially, copies of what it thought these images were. And this is what popped out on the other side. So this is almost like watching a computer dream. So this is a really neat feature that this class of models has, is that they can not just classify, they can also generate. The objective function, when you're training this, though, as I said, you want to end up changing these connections. And the objective function that you, in practice, want to optimize is the average log likelihood of the data being generated by the model, which is, in principle, given by these equations. I won't spend too much time dwelling on it, but there's one feature that's very important, which is this over here. And for people in physics, this is the log partition function. And this is really problematic because the objective function we want to optimize, turns out it's sharp p hard to actually compute exactly. And so what that means is if you want to do a naive approach and figure out how to increase your log objective function, what you could do is you could imagine changing these weights, these biases and weights in this E term up here, and compute a gradient just by a divided difference. You evaluate it at one point, you evaluate it at another point, subtract the two, and you've got a gradient. But the problem is this log z term over here can't be computed practically. And so what has to be done is, rather than exact computation of this, we really have to try to do a gradient descent on this using approximations to the log likelihood function. That's the only way to make this happen. And so the first method to make this really kind of practical was Hinton's contrastive divergence algorithm in 2002. It works wonderfully, and it's what people still use when training Boltzmann machines. But unfortunately, it's extremely crude of an approximation. At least the lowest order is extremely crude. And if you want to increase the accuracy of this, it's prohibitively expensive. So much so that in all practical cases I've been able to find, people only use the simplest possible contrastive divergence approximation. So that's a bit of a problem. And so the question is, well, if it seems like it's prohibitively difficult to generate a high accuracy approximation to these gradients, the question is, can quantum help? And the intuition that I had going into this was, if quantum computers are really good at simulating physical systems, it stands to reason they may be able to provide some advantages for simulating sampling from Gibbs distributions, which is, well, something that people in the audience, in particular David Poulin and other people, have looked at in detail. So here's the idea for quantum deep learning. The basic overview is that what we do is we provide a quantum algorithm that approximates the gradients of this log likelihood function and does this more accurately than the contrasted divergence algorithm, or at least low-order contrasted divergence algorithms. And the intuition behind it is as follows. What we do is we begin with an approximation to the Gibbs state that ends up, or the distribution over that the model ends up sampling from. And then we use this process called quantum rejection sampling, again, very similar to the concept that you came up with, to refine this distribution into a copy of the exact distribution we want, or something that's very close to it. And the probability of success for this process ends up depending on the ratio of the probabilities predicted by your approximation that you feed into this, and the probabilities that you want popping out the other side in this branch. So the idea behind this is you prepare a quantum state that approximates the solution, you feed it into this quantum refinement algorithm, and then you flip a coin, and with some probability it'll work, and you'll get the actual true Gibbs distribution, and with some probability you'll fail, and you'll just have to repeat again. So you just keep on going through this process until finally you end up in the right place. That's the intuition. And then from these samples, you can estimate the gradient of the log partition function. So that's it. You turn gradient calculation into a sampling problem and use a quantum computer to provide you with the samples. Now, that's not entirely fully it, because you can further optimize this. There's these algorithms known as amplitude amplification and amplitude estimation that can be used to quadratically increase the probability of success for these circuits. And on top of that, can quadratically reduce the variance of any estimate of the probability of the samples coming out. So this can actually lead to quadratic reductions in the cost, even on top of everything else. So we use these in order to further optimize our quantum algorithm. And so to look at the high-level view of this, what we do in practice is we begin with an algorithm, or approximation to the actual distribution that the model provides, known as the mean field approximation. Then after we've computed this approximation, we prepare the mean field state in the quantum computer. Now we do something that looks like it ought not to be classically simulatable at all. We compute the energy instantaneously for every configuration that the system can achieve. So for this 1,000 thing, there's like 2 to the, for the Hinton et al. Image that I showed previously, there's over 1,000 units. So the number of different energies that have to be computed is 2 to the 1,000. Yet the quantum computer can do this instantly. And so we compute all of those, and we use these energies in order to refine the distribution, using the quantum rejection sampling into the true distribution that we actually ideally want to sample from for the Boltzmann machine over the visible and hidden units in the graph. Then, once we have that quantum state, we measure the quantum state, and we get a sample from it. Once we've got that sample from it, then we repeat this process over and over and over again and develop statistics. Then from those statistics, we can compute the gradient in terms of the expectation values of the combinations of various visible and hidden units in this. So we just use these samples, plug it into these formulas, and then we can find the gradients. And then with those gradients, we can start marching uphill towards models that are better and better and better, and thus find a locally optimal solution. The other thing that's neat about this is that unlike many of the other quantum machine learning algorithms, the data doesn't actually have to be stored here in a quantum RAM. We can sequentially feed in each training vector. So this means that unlike many other proposals people have done so far, you don't need gigabytes, or gigacubites, I guess is the appropriate words. You can get by with just maybe 100 qubits of input for actually physically realistic problems. So that's pretty cool. if we take a look at the complexity, the advantages, though, that we end up getting out of this, they're polynomial compared to contrastive divergence. So exact training using is inefficient, as we expect, because of the sharp p hardness. So the contrastive divergence ends up training linearly with the number of training examples, linearly with the number of layers, linearly with the number of edges in the graph, and this k over here is the number of iterations for it. So for all intents and purposes, just imagine k is 1, because that's all people use in practice. If we take these over here are different variants of our quantum algorithm, and a key point is that what we do is we have this kappa parameter, which is an accuracy parameter. But the key point is that we don't actually have scaling that depends on the number of layers, because of the fact that we don't have to greedily train with this algorithm. So that gives a pretty big advantage, because if you're looking at an incredibly deep network, we don't pay a price for the depth. We only pay a price for the size of the graph. So that's a key thing if we really want to take these to very deep networks. The other thing that's really kind of neat is if we do give ourselves the ability to store the training data in a quantum system, then we can use amplitude estimation in order to give you estimates of the components of the gradient much faster. In fact, the thing that's really surprising about it is that if you have n training vectors, you only have to query the memory square root of n times, which sounds like it ought to be impossible. But it turns out through the magic of Grover's search and phase estimation, it's not. And you can actually learn off of effectively the entire data set by querying it fewer times than there are training vectors. So that's something that's really kind of neat that quantum gives you on a conceptual level that you don't end up getting classically. So key point is we end up getting a quadratic reduction for that scaling, and also the cost does not directly depend on L, because we're not forced to do greedy layer by layer training with this method. However, again, there's questions about how we approximate the Gibbs state and how this approximation leads to couples into this value of kappa here. This value of kappa, which is the accuracy parameter, if we needed an exponentially large value of kappa in order to give comparable accuracy to contrastive divergence, then there's very little benefit to this, except maybe in some special cases. And so the question is, how well does this work? Well, we use the mean field approximation largely. We also have proposed choosing product distributions that minimize different variational distances. These scale better, and I can talk more about those during the question period. But in any case, the mean field approximation works very well for dealing with this. And it matches the probabilities predicted for the actual by the actual Gibbs distribution extremely well for practical machine learning problems that we could test. It works very well for the coarse features. It doesn't work quite as well for the fine features. And this is what we need this idea of quantum rejection sampling in order to refine. Because although it does very good matching this peak to that peak over here, if we really want to get this to generalize into the well, then we need to actually also hit these low probability peaks. So that's what we use this for. And the moral of the story is, it works pretty well. This value of this over here could be thought of as the quality of the gradients, and this over here is, can be thought of as the quality parameter that you tune. And so as you increase this quality parameter, values of about 100 seem actually to provide extremely good estimates of the ratio. So what this is suggesting a mean field approximation, at least for the trained examples that we could handle on our ordinary computers, works quite well. So the mean field approximation seems to be doing it. However, other approximations are possible in cases where strong correlations exist. Okay, it also works for the full Boltzmann machine. And also, it leads to significant improvements in training accuracy over contrastive divergence training, which plateaus out. Our method continues to learn. So before concluding, I'd like to say one thing. This is talking about what we can do in the quantum case. I mentioned that this feeds back into the classical case. It turns out that with a quantum algorithm, what we do is we prepare the quantum state, then we refine it into the ideal quantum state that we'd want, then we draw a sample. We can actually think, by changing the order in which we measure these two things, we can actually convert our quantum rejection sampling into classical rejection sampling. So instead of sampling at the end, we sample in the second step. Then we check to see if it's right. So that's basically the idea behind our classical algorithm. And a key point behind our classical algorithm is it retains all of the nice features that our quantum one does. It has better scaling with the number of layers. It can provide high accuracy, and the most importantly, the depth is low. So the contrastive divergence training scales poorly, the depth of it, with the order of contrastive divergence training and the number of layers. Ours doesn't. So it parallelizes much better over a cluster than contrastive divergence training does. So this is really kind of a neat property that ends up coming out, that thinking about quantum algorithms actually ended up leading us to a new classical algorithm that didn't seem to exist in the literature and seems to have benefits that over existing methods. So in conclusion, what we provide is we show that quantum computing can be used to provide polynomial speedups for an important class of machine learning algorithms that actually people want to use industrially. Furthermore, this leads to this thinking about quantum algorithms for machine learning actually gave us some new insights for machine learning in the first place, which led to new algorithms that in some cases may provide advantages over contrastive divergence training. And I think if there's a take-home message about this, it's that quantum computing isn't necessarily all about giving speed-ups. It's also about providing insights. By looking at it from this perspective, we forced ourselves to ask a question about what it means to learn and what is the basic nature of machine learning. And this led to some insights that provided new algorithms. And so I think that, going forward, quantum machine learning will probably be just as important from a foundational perspective as it is from a practical perspective. Thank you very much.
Great, thanks, Nathan. So I'd like to invite our speakers up just for a few questions from the audience. So we have Matthias Treuer, Eddie Farhi, and we've just heard from Nathan Wiebe. So if you have questions, we have some runners with mics. Looks like the first hand went up over here, if we could get that question.
Well, actually, I can shout. Yeah, right. So I have a question to Matthias, and I'd like to thank that you touched upon chemistry because I'm a chemist. Yeah. So the question is that in traditional traditional quantum chemistry, some sort of classical computational chemistry, yeah, certain things can be easily done, and there are some algorithms out there. And my question is, how can you combine this powerful diagonalization engine to conventional algorithms for dynamical correlation, for instance, and so what is your kind of perspective on the future computation? I don't think that shipping everything to quantum computers is a good idea.
So what we have in mind is the hybrid machine, where most is classical, and then you identify the subspace of the correlated orbitals, and there you would now do the full CI calculations, for example. But they are hard classically. And so now we want to do the full CI part on the quantum machine with 200, 400, 600 active orbitals, and then use that to get the better solution of the quantum system. You still have to find the active subspace, solve it, feed it back, improve it, and learn. And this is just the first step. Now we need to think of more ways how to feed it back, improve it, integrate it. One could also use it for better force fields, better functionals.
Do we have another question? Yes, right here.
My question is for Eddie. So when you have the superposition of these wave functions, like in your particular problem or any similar problem, when you define an operator, what is the physical manifestation that you're looking at? My question is, how do you engineer that operator to work on that wave function? Is there a way that you guys can perceive doing that?
The question is, I don't know, can I be heard? I'll scream. Yeah, the question is, how do you actually implement, let's say, the phase operator where, well, first of all, thank you. Thank you so much. Well, first of all, any calculation you can do on a classical computer, you can do on a quantum computer, any function evaluation. So with a little caveat, but it's fine. I mean, so evaluating the function is something you can do. Then there's a trick, which you learn in quantum computing, for how you can take the value of the function and put it upstairs. In other words, e to the I times the value of the function. There's a standard trick for that. I mean, I could, in 10 minutes I could show you how to do that. It's a simple circuit, but the key ingredient there is that you can call the function classically, which means you can call it quantum mechanically, and you can put the phase upstairs. Does that help you a little?
Yeah. I'll read your paper. I'll understand better.
I don't think in my paper we're going to show that,
but
because if you read in a standard textbook on quantum computing, they would show you how you do that.
Okay.
Yeah.
Sure.
Is there one more question? Great.
Yeah. This is a question.
I don't want this to sound like a criticism, and I'm not a quantum guy, but is this on? Can you hear me?
Yes.
All right. Is comparing to the top 500 list in terms of parallelism the right place to go? It seems like numerical linear algebra, inverting matrices, is not where we're going with quantum computing. That's not an algorithm that we have. And so is there something better that can excite people about the kind of problems that quantum computing will solve?
If I could answer this.
Okay, yeah.
Well, I think actually to some extent that your choice was a poor one, because inverting matrices is actually one of the things that we do have a good algorithm for, at least in the case of sparse, well-conditioned matrices. There is an exponential speedup for that particular problem. However, speaking more broadly about how we should compare quantum to classical resources, this really isn't actually good at the moment, because at present what we usually end up doing is we end up saying, all right, let's look at this in an oracular model and compare function calls that are made in one setting to function calls that are made in the other one. Really, what we want to work towards is a case where we could compare dollars for computing one value versus dollars for another one. There's a number of steps that we need to make along the way, and people in our group, in particular, I'd like to call out Dave Wecker and Alan Geller, have been doing a great job for getting us partway there and being able to break everything into atomic operations that we can compare one to one. And from that perspective, we could literally compare, if you make assumptions about the run times of a gate operation, we can at least compare time. Now, we're a long way from figuring out dollars, but I think that's where we need to be in order to really answer the spirit of your question.
Okay, and to let me add one thing is that what we want in the end, we want to be able to do things that we'll just never ever be able to do on any classical machine. That's the goal in the end. But to reach that, the benchmark has to be at least the top machine on the top 500. If that machine has an easy time, then we're not there yet. We have to go way beyond that. And not just say, okay, it's faster than one core on my smartphone, but it has to be really better than the best we can do with standard classical chips. Then we start being in business. In the end, yes, we want much more. I fully agree.
Let's thank our three speakers. And thank you all. Our speakers will be wandering if you have more questions. Thank you all for